Welcome to the Phase Transitions Part 1 screencast. The objectives of this screencast are to describe the liquid-gas phase transition, to define vapor pressure and boiling point, and to predict the effect of intermolecular forces on vapor pressure and boiling point. And let's start with a container of liquid bromine, and you can see here that the liquid bromine actually has some of it turning into gaseous bromine. And we have here what's happening is that molecules escape from the surface and form a vapor. Some of these bromine molecules that are in the liquid form have enough energy to become gaseous bromine molecules. So here's a little schematic of this showing molecules in the liquid form, molecules in the gaseous form escaping from the surface and forming a vapor. And if you remember the Maxwell-Boltzmann distribution of number of molecules and kinetic energy of those molecules, it looks something like this. And for a given substance at a given temperature, there is a minimum energy, minimum kinetic energy, that the molecules need to be able to escape the surface, overcome the intermolecular forces between the molecules, and turn into a gas. So here it's represented by molecules with energy beyond this point. Now, if we take our whatever substance, in this case our example is bromine, and we seal the container and let the gas that's outside this container escape, now we have a closed system and we end up having liquid molecules and gaseous molecules form an equilibrium. And we can actually measure the pressure of the gas for a given substance at a given temperature, and that is what we call the vapor pressure. The vapor pressure is the partial pressure of a gas in equilibrium with its liquid at a particular specific temperature. Now, if we end up taking our substance and cool it down, we reduce the temperature, what ends up happening is we have less molecules that have enough energy to escape into the gas phase, and the pressure of the vapor becomes lower. It decreases. Now, conversely, if we take our substance and heat it up, if we increase the temperature, then what happens is we have more molecules that have enough kinetic energy to escape from the liquid, become gas, and our vapor pressure becomes higher. It increases. If we again look at our kinetic energy versus number of molecules distribution and our minimum kinetic energy to escape from the surface, we see that at a lower temperature there's a smaller number of molecules that have enough energy, and at a higher temperature we have more molecules that have enough energy, that minimum kinetic energy needed to escape from the surface. And so that kind of explains the difference we see in the vapor pressure at different temperatures. And in fact, if we do some measurements, determine at a variety of temperatures for a given substance what the vapor pressure is like, we get a curve of vapor pressure versus temperature that looks like this. And in a later screencast, we'll look at this in more detail mathematically. For now, just the general shape of the curve is sufficient for us. And above this curve, when we have temperature and pressure values somewhere in this region above the curve, that corresponds to having a liquid. And if we're below that, we have a gas. And if we're on the line, we actually have an equilibrium between liquid and gas. And at any given temperature, we have a corresponding vapor pressure, and at a given temperature, that vapor pressure is a specific value. And when we have a liquid and we heat it up to the point where the vapor pressure of the liquid, so here the liquid has its vapor pressure, equals the external pressure on the container, then we end up having the liquid boil. So in most cases for us, that's going to be when we have an external pressure of at 1 atmosphere, or if you're at a higher elevation, perhaps a little bit less. But we'll have, when we reach a temperature sufficiently high such that the vapor pressure of the liquid equals the external pressure, we get boiling. If we go to a situation where the external pressure is less, we end up having boiling occur at a lower temperature because that corresponds to a lower vapor pressure. So going back to our curve again, here's the vapor pressure curve versus temperature, and typically at 1 atmosphere, if we're at sea level, that is the external pressure, and here is the point where we have the boiling temperature corresponding to 1 atmosphere vapor pressure for that particular substance. Now, of course, this is all related, both vapor pressure and boiling point, to strength of intermolecular forces. So let's take a look at a couple of substances. We'll start with substance B, the curve we've just looked at, and at a particular vapor pressure corresponding to whatever outside atmospheric pressure you have. So let's say 1 atmosphere. The boiling point of substance B corresponds to the temperature at this point. Now, suppose we have substance G and it has a vapor pressure curve that looks like this. Well, the atmospheric pressure, 1 atmosphere here for substance G, corresponds to the temperature shown with the dotted line on this graph. And that, of course, is a lower boiling temperature than the boiling temperature for substance B. And that lower boiling temperature corresponds to substance G having weaker intermolecular forces. So there's weaker attractions between the molecules. They're easier to overcome. And so at a given temperature, we can end up having we can have the substance boil more easily at a lower temperature in comparison to substance B. Now, if we look at the vapor pressure curve for substance R, we have to raise substance R to a temperature shown here by this line, and that's where it's going to boil at a much higher temperature because we have to get to this temperature before the vapor pressure equals the external pressure, and that, of course, corresponds to stronger intermolecular forces. And we've seen this before. Lower boiling point corresponds to weaker intermolecular forces. Higher boiling point corresponds to stronger intermolecular forces. This just sort of ties it in, though, with the definition of what is required for boiling to occur in terms of vapor pressure of the liquid equaling the external pressure. Now, conversely, if we look at things from the perspective not of boiling temperature, but just simply vapor pressure, if we pick any temperature we'd like, so here I arbitrarily picked this particular temperature, and we see what the vapor pressure is at that temperature for substance R, substance B, and substance G. Let's start with substance B, the one in the middle, and at this particular temperature, the vapor pressure of substance B is shown on the graph here. Now, substance G, which we've already realized, we've already determined it has weaker intermolecular forces, notice at this particular temperature, it has a much, much higher vapor pressure. So weaker intermolecular forces actually correspond to a higher vapor pressure. If the intermolecular forces are weaker, then they're easier for the substance to overcome, and at a given temperature, if the intermolecular forces are weaker, more molecules can escape from the liquid phase, turn into the gas phase, and exert a higher pressure. And of course, the opposite occurs for the substance, this case substance R, that has a vapor pressure curve that is lower than that of the other two substances. Substance R, we've already discussed how it has stronger intermolecular forces, and therefore it has a higher boiling point. But in this case, because it has stronger intermolecular forces, that means it has a lower vapor pressure. So stronger intermolecular forces means less molecules can have enough energy to overcome the intermolecular force, escape from the liquid, turn into a gas, and therefore we have a lower vapor pressure for the substance with stronger intermolecular forces. And that is it for the phased transitions part 1 screencast.